Lauren from non-equilibrium spectroscopy. I've had the good fortune of being in a session where several people have done an amazing job introducing non-equilibrium physics better than I ever could, so thank you guys very much. It'll save me a little bit of time. And I'd also like to thank the organizers for giving me the opportunity to come present some of our results in this forum. Okay. This one is backwards. So I'd like to thank my collaborators for their support in this work. I work together with Michael Sentev, who is now at the Max Planck Institute in Hamburg, Jim Frevix, who is here, Brian Morris and Tom Devereaux at Stanford, and then we have some experimental colleagues for a bit that I'm going to talk about later, where the experiments were done in the lab of Uwe Bovensiepen, and were performed partially by John Rameau, who is a Brochet. So this is sort of the brief outline of my talk. I'm going to talk about materials in general rather than material specific. I sort of talk about how non-equilibrium is different, how it is the same, and how we can use this to our advantage. So I'm going to talk a little bit about electron-boson interactions, particularly electron-phonon, and how this relates to population decay rates, which is something that's commonly measured, as Rick was just showing us. I'm going to talk about Matheson's rule. I may remind you what it is, and then I'm going to tell you how it might not apply in the time domain. And finally, if I have time, and I'll do my best to have time spurred on by the questions earlier, I'll talk about Higgs oscillations in D-wave. Okay, electron-boson coupling. Quite generically, it looks like this. Because I'm a theorist, that's what they all look like. And this thing leads to all sorts of interesting physics. Right? In our correlated condensed matter systems, we have phonons, we have magnons, spinons, orbitons, any kind of ons that you like. I'm going to focus on sort of a generic model which includes everything. We've got some electrons, we've got some bosons, they couple together, and the electrons might interact amongst themselves as well through the Coulomb interaction. And when you put these together, depending on the material, you get a couple different types of physics. One thing you get is when you have a singly strong interacting boson, you get kinks in the quasi-particle dispersion. Jim talked about this a little bit earlier. Here I've pulled some data related to the cuprates, which are certainly a correlated material. And you see that the dispersion at roughly the boson energy has a kink. It goes from one slope to another. This has now been discussed for quite some time. And people have associated it with bosons in this material, quite often with a phonon that lives at 70 millivolts, although depending on who you talk to, the jury is still out. So we'd like to know sort of, what is the origin of these interactions, how does it affect the quasi-particles, and ultimately how does it affect the correlated states, the emergent states that we find in our materials. Let's see, so we see kinks in dispersion, from which we can extract something about the interactions. In this case, this is an extraction of the real part of the self-energy. The interactions also determine the quasi-particle lifetimes, from which we can look at the electron lifetimes via alignments. So Jim showed this picture earlier. This is again for sort of generic single frequency boson in Einstein mode, where you have a scattering rate that drops to zero. Oops, my axis has gone near the Fermi level. And then at plus and minus the phonon frequency, it jumps up. And this is going to be important for the talk, so I'm going to mention this in a little more detail. What this essentially comes from is phase space restrictions. If I have a system that's in equilibrium, I've got the band, this is my band structure below the Fermi level entirely occupied, I've got my band structure above entirely empty. And if I am a singly excited quasi-particle that sits here, I can't really decay over there because I don't have any space to do so. All my states are occupied, and so I'm sort of blocked from doing this. And that's true anywhere within this phonon window, assuming I'm using this one phonon as my decay mechanism. On the other hand, if I'm above this phonon frequency, I can easily scatter down, no problem. And that's the origin of this jump up at the boson energy. So now in the time domain, one of the questions that we originally arrived at was, well, could we go and measure this? But in the time domain, it's a lifetime. Could we do this? So there's been some experiments that have attempted to do this. Oops, from both sides of the ocean, where they've looked at the dynamics of, in this case, time-resolved darkness. So I'm not going to go through it, Jim went through it. But we're going to try and use theory to simulate this. He also went through our non-equilibrium Keldysh formalism. I'll briefly point out a couple details. You start from the thermal state. You propagate it forward in time. This whole system knows about the history. It knows that it came from a thermal state. It knows that a pump field was applied to it. And then we make some measurement here. Our interactions are encoded through a self-energy, which we can put all sorts of things in that we like. And we include the field through the pyro substitution. And this is sort of the results that we get. So this is one of our earlier results. This is work that I did together with Michael Sinta. Let's see if I can make this go. There it goes. So we have an ARPA spectrum that, as the pump arrives, produces some excitations above the Fermi level and then decays. This is purely electron-phonon interactions. This is all we have in the system. And we did some work where we looked at time traces of momentum-integrated ARPAs and saw that stuff inside the phonon window went much slower than outside. And that reminded us of this. And we made this sort of connection that Jim also made, where we could say, well, if you look at 1 over tau, as determined from these, as a function of frequency, you basically get the imaginary part of self-energy. So that was great, but it still left some questions. And one of the questions that we got was, well, how about pump fluence? How does that affect these results? Or, what if we tried more power? Now, when you make this excitation, right, this is sort of this traditional picture that I stole from Patrick Kirschmann, I think, where you take some of your spectral weight below the Fermi level, you move it above, this might equilibrate a little bit, you've got non-thermal electrons, and you end up eventually, through electron-electron actions, with a new Fermi distribution. So we should really account in our calculations for the changes self-consistent. For the theorists, that means I am now doing self-consistent Born approximation. And what this leads to is changes. So here's our results again. In the limit, basically where you are at such low fluence that you are not affecting anything at all. And now we're going to turn up the fluence, and we're going to take care of this redistribution of quasiparticles. So here are the same sort of things where we fit 1 over tau. And Jim showed this as well, where as I increase the fluence, I end up with changes in the scattering rate. Excuse me, changes in the population decay rate, because that's what these are. This strong pumping reduces the population dynamics on the outsides of the phonon window, and it slows them down and speeds them up on the inside. So we have this relation which turns out to be kind of approximately true now, or at least we have to think about how is this modified in the presence of the pump, where this happens if I make a lot of excitations, a lot being determined in this case by, well, how far away do I get from this picture. This comes with an apparent decoupling that Jim talked about, and I'm going to talk about the origin of this a little bit. This is my equilibrium picture. Now in non-equilibrium what I get is I've just redistributed some of these guys, which means that this scattering rate, which was previously forbidden, I can now do. This one, which was really easy, is now a little bit harder, and that causes this change in the scattering rates. Just a phase-space restriction at this point. There's some experimental evidence for this from several groups. This is from the Lanzara group, this is from the BNL group, and this is from the Shin group in Japan, where they've seen changes in the King structure, which they attributed to a decoupling of the electrons and phonons. As Jim pointed out, this is actually not what's going on. And here they see transient changes in the line width. Right, so the self-energy is being affected because you're redistributing the electron population. Okay. So that was the story for a time being. And then along came this nice work from the Stanford group, where what they did is they compared what you would get for the lifetime if you did equilibrium ARPAs, where you look at the MDC line width and you see what the lifetime is from there, and you compare this to the population decay rate at roughly the same energy. Here's what they found. Okay, so this is the data, this is the analysis. If you look at the quasi-particle self-energy as determined by MDC line width, these are sort of the numbers that you get. It's 20 Kelvin and 120 Kelvin. And this is in 2212. If you look at the population decay rate, which I've been telling you is ostentatiously, or it's supposed to be the same thing, ostensibly. When they look at it, they see that it is different by not a small amount. It's actually quite a big amount. So this relation that I had between the population decay rates and the single particle dynamics were sort of thrown into question. Right? We had something that was roughly the same, and this is completely different. So we can think about this a little bit. Where do these things originally come from? What are they? Well, 1 over tau is measured by making an excitation, looking at the quasi-particles, looking at where they are, and seeing how they return to equilibrium as a function of time. The equilibrium self-energy is really about how does my single particle decay in the presence of all the many-body physics that's going on within my material. These are very, very different things. In the language of Green's functions, right, we normally think of this as the possibility of making an electron here and observing it sometime there. For a sort of very simple model, if I look at what this looks like, normally we think T minus T prime, that's all I need. Doesn't matter when I make the excitation. And that's this sort of direction. Right, I can do my measurement now, I can do my measurement tomorrow, unless I'm looking at one of these metastable states. And I should really get the same life. So this is where we get, from your many-body physics 1, this equilibrium self-energy that arises from this T minus T prime direction. On the other hand, when I do a time-resolved experiment, I have a time zero. I have a now. That is determined by when the pump arrives. And that means I get changes in this direction. This is an equilibrium picture. There's no changes in this direction. The cut here will produce the same data here, the same data there. I would have the same sort of Green's function. But if I do a time-resolved experiment, stuff is different along this direction. And along this direction is where your population dynamics come from. Right? Because that is measured as a function of real time, of where your experiment is being done, rather than relative time, which is when do I make the quasi-particle and when do I miss it. This is what we normally Fourier transform. Right? So when you think of a line width or something, that comes from here. So this has consequences. And the way we see this is by going beyond our picture of just electron-phonon scattering and start doing some other things. So these are the typical ones, and these are the ones we chose to work with. And so I'll show you some of the results. So on the left here, I have electron-phonon scattering. You've already seen this. I have an excitation, there it goes, and it returns to equilibrium nicely as a function of time. This is impurity scattering. It starts from there, I make some excitations, and that's it. There's no decay, there's no return to equilibrium, it just hangs out there. This calculation stops at this point, but really it doesn't go anywhere past that either. So, what was going on? Let's see what happens when we take both. So what I can do is I can do the normal sorts of things, and I can calculate what my self-energy should be and what my spectrum should look. So this is where I've taken just electron-phonon scattering, no impurities. This is what my spectrum looks like. I've got a nice kink. I've got the self-energy, which has this phonon window. And now I start adding impurity scattering. And sure enough, my spectrum gets nice and broad. My self-energy loses this gap in the middle because it doesn't exist anymore. It's being filled up by all this electron impurity scattering because of Matheson's rule, right? Scattering rates should add. If I go to non-equilibrium, and I now do the same thing, where I make an excitation, I look at the population, I hit its decay rates, here's what we gain. So this corresponds to the point above. This is sort of what you saw before. Where I have this window where the phonon energy sits. And now as I start increasing, my electron impurity scattering. There it goes. I maintain the phonon window effect, and in fact I barely see any change in my population decay rate. These things are clearly not the same. My self-energy is not the same as my population decay rate. Well, why not? Let's think about it this way. I've got a system of electrons, and I've got light coming in, right? So suppose I have one electron that absorbs a bunch of light, or one subsection of my electrons. Those thermalize maybe a little bit, and then if there was nothing else going on, they would sit there at higher temperature. What I need to return to equilibrium is a heat path, right? And I need to couple to this heat path. So eventually, some of the energy transfers here until these guys are in equilibrium. So really what determines my population dynamics is how do I get energy out of my electrons. And in the situation I just showed where we had electron-phonon scattering, electron impurity scattering, phonons are the only ones that can do that. And so the decay rates you see for the population are entirely determined by the phonons. So now for electron-electron interactions. This is a situation where that's all I have, just electron-electron. And I'm going to do the same thing. We're going to make an excitation. There it goes. And then it relaxes, and it sort of stays. And what it relaxes to really is basically another thermal state. Right? I've got pumped energy into it. It's got higher energy. The electrons thermalize amongst themselves. And now I have a new state with a higher effective temperature. Great. That's been done for a long time. So here's the two cases again. Here I have electron-phonon. Now I have electron-electron. These are snapshots, and we're going to combine these. Now, before I start combining these, actually, let's look at the energies, right? So here, what I should see, if I look at the total energy in the electrons, I should see an increase and then a decrease. And here, after the pump is gone, my electrons maintain their energy, right? They can only scatter with each other, and so this should stay flat. And that's really what it does. The blue curve corresponds to a pumped electron-phonon system. I put energy in, and it slowly goes out as it loses energy to the phonons. The red one is electron-electron, where I absorb a whole bunch of energy, and that's it. There's still thermalization going on in here, but you can't see it in the total energy, right? Because that's just going back and forth. So really, it's energy transfer that determines this. So let's look at the combination again. Here's the same plot of one over the decay rates. And this is for just electron-phonon. It's got the phonon window effect, it's got everything you expect. So now I start adding electron-electron scattering. Initially, it appears to go up a bit on the high side. Nothing happens here. It still stays a little higher, and then in fact, it starts to drop down on this side. But I still maintain a step in the electrons. Right, up to the point where these guys are comparable, I even still have most of the shape maintained. The absolute shape value is a little different, but the step stays the same. There appears to be some competition. Right, because if these guys were to just simply add according to Matheson's rule, well, I would get my electron-phonon curve, and then I would get on top of that whatever the electron-electron thing is. That's not what's happening. Right, these guys should be manifestly positive, or at least imaginary part of the self-energy should be manifestly negative, and yet I see these guys with opposing signs. They compete. So Matheson's rule does not appear to hold in non-equilibrium. So, to convince you that this is not entirely off in theory land, we have some experimental results on this as well. This was together with all of these guys, done in Uga's group and led by John Ramon, where they did time-resolved photo emission on cuprates, which we're pretty sure are correlated. Right? Electron-electron is kind of important. And they did the usual business where they took a time-resolved spectrum. This is a different snap. You can still kind of see the phonon window effect. They looked at population decay rates. And this is the theory picture we had. This is the experiment where the relevant phonon lives at roughly 70 millijoules. Now, if you look below, you can see that for low fluence, the blue curve here, this is fast, slow, and the red one is fast. Above, we've got the opposite. For low fluence, I have very fast relaxation, and for high fluence, the red curve, I have slower relaxation. So this somewhat agrees with our picture, and in fact, we can play with our parameters a bit and end up with something that looks very much like their results. Sort of a pink at, or change at 70, and sort of similar colors as you go. We can go a bit further, we can do some analysis. Here's tau from the experiments as a function of energy and fluence. You see this step at low fluence, and that step sort of softens at high fluence. This is a theory picture, or really the upside down version of that. And we actually get a reasonably good agreement. Now, one important thing is that the only thing I have in this theory is electron-phonon scattering. That's it. There's no electron-electron. And yet in this material, which is cuprates, where electron-electron is pretty important, we managed to capture a very good portion of the dynamics entirely with just the phonons, which are, after all, responsible for taking the energy out. Okay. So the take-home message from there is, if you can see some kind of fingerprint of a boson, it's probably taking energy out of your system. How much time do I have? It's 5 minutes. Okay. So in that case, I'm going to talk about Higgs and D-wave. Jim has already introduced this. It's a very old story. In this case, paper in 1973, and the basic idea is that, actually, let's do it this way. So if you look at classical theory of phase transitions, this is a very simple one, right? What I start with is some high temperature free energy, and as I start decreasing the temperature, I eventually hit a point there where my free energy curve is below zero. I go through a phase transition until eventually this is my free energy at low temperatures. This is a superconductor, so this is a two-dimensional order. And in principle, I should have oscillations this way, which correspond to this side, and then some kind of free phase oscillation, which in the presence of electron-electron interactions gets gapped out. So an amplitude mode would be something that's down there, and I can somehow perturb the system, and it sort of wiggles back and forth. The problem is, in equilibrium, this does not happen, because the superconducting order does not couple in linear order. It doesn't couple to light, it doesn't couple to all sorts of fields in linear order. So the idea in non-equilibrium is to do the following. Let me take two sort of potential surfaces, and rather than adiabatically with temperature slowly going up there, make this happen quickly. At this point, the system doesn't have enough time to respond in this adiabatic fashion. I excite sort of vertically, and what I would get is oscillations about the new minimum. And that's what we see. This is what Jim presented earlier. Find oscillations at 2 delta. The important point, which connects to your talk earlier, is that you should not entirely melt your order, otherwise you wouldn't have any superconductor lift to oscillate about. Right? You'd be about here and you wouldn't see anything. So D-wave. This is work done together with Ben Nazarewski, who was at Stanford. So this is, I'll just go through this very quickly. This is a nodal cut. It's sort of hard to see, but there are some oscillations present. I'll show you the difference in a moment. But at the node, of course, there is no gap. I should still have a shift of the phonon frequency, which we do see. And if I go to the difference plot, you don't see it at the node very much because I don't have a gap there, but at the gain position, I have clear oscillations. We can do similar sorts of analysis as we've done before. These are EDCs. And I can pump these guys. And you can see that at the node, basically what happens is you just sort of reduce your signal and it comes back. At the antinode, however, at the antinode, it sort of wiggles back and forth. So we can do the analysis. We can look at what the gap size is, a function of momentum. Right? It follows this standard D-wave form. And then if you pump this, what you get is this sort of. You see a reduction in the gap. Doesn't exactly follow the D-wave form, it kind of does. And then you see some wiggles. In the interest of time, I'll make it quick. We can do all sorts of analysis. You can see oscillations in both in the EDC maximum, this dot there, as well as the kink position. And the point is that these oscillations are isotropic in frequency. Doesn't matter where you sit along the Fermi surface, I see the same frequency. That being of the antinodal gap. In particular, it being the antinodal gap after I've pumped the system. In other words, how much superconductivity is left, those are the oscillations we're going to see. So we can do the same game where we do this as a function of fluence. Right, for very weak fluence, I make small changes, and I get very weak oscillations. For larger fluence, I make big changes, and I see bigger and also slower oscillations. So you can plot the oscillation frequency as a function of, in our case, applied field. Really, you can convert that to how much energy is absorbed. And this extrapolates out in some simple polynomial form to the equilibrium to delta, as it should. Okay, so in summary, non-equilibrium time domain is different. Right? We may see different things that we weren't expecting. In particular, Matheson's rule is not something that holds. Interactions may have complex interplay where they may work against one another. They may compete. The main dynamics you see in terms of population transfer are how do I get my energy out, so energy transfer. And the cool thing is we can use this to separate out various interactions. If I do equilibrium spectroscopy, everything gets sort of mushed together. Right? If I try and extract my self-energy from ARPES, I will get all of them. Impurity, electron, 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 phonon. Here, I can turn this around and say, well, if electron phonon is the only thing that gets my energy out, then I can separate this from impurity scattering. It doesn't play a rolling role. So that could be useful. Be careful looking at all changes with equilibrium language. Everybody probably knows this by now. And at the bottom, it's cut off. Our calculations for D-wave superconductors also appear to show Higgs oscillations. They are not. They don't appear to be damped any faster, which is kind of interesting, but we don't quite know why yet. And that was it. Thank you very much.
Thank you, Lex. The talk is now open for questions. Yes.
I have a question about the Higgs oscillation.
Sure.
So when you say that you excited from this original free energy into the other one that looks like at a higher temperature.
Yes.
Is my understanding that it's just heat up the sample, then after a while shouldn't it just cool down? Shouldn't it slowly oscillate? Somehow while it's oscillating, shouldn't it comes back?
Sure.
To the original? It
Sure.
doesn't look like it's...
So 2 points. One, that was sort of a cartoon picture.
I see.
Right, we don't actually have increased temperature. We have non-equilibrium redistribution, blah, blah, blah. On the other hand, yes, you are correct. We should see a change in the frequency. It should speed up as a function of time. And it's hard to see here, but if you do the analysis, you can actually see that the oscillations here, this one's a better one, I think, are somewhat slower than they are over there. We have some other data that shows us a little bit better. So yes, the oscillations do in fact speed up. Peter?
With your depopulation and the analysis of the impurities, have you always looked at the simple parabolic band? What about the combination of that and parabolic band?
So for the moment, we've been limited to cosine band, cosine single bands, but we're working on multiband. It's on the docket. See?
Andrew? So without superconductivity, there's a little local maximum of imaginary self-energy right around the Fermi level?
Yes.
And is that because of electron-electron interactions? Or
No, you get that from electron phonon by itself. Let me see if I can find this quickly. Oh, here we go. Right there. So that's electron phonon only. We do see that. I can't say I have an amazing picture as to why this is. It is a reflection of the fact that this is a non-equilibrium distribution. If we're equilibrium, what you would have is you would have a Fermi function on the left and a Fermi function on the right and some sort of overlap between the two. But because these are non-equilibrium distributions, which determine the self-energy, you get this odd stuff in the middle that you otherwise wouldn't get.
So, at the start of your talk, you said a boson. Sometimes you kind of said a boson to boson in your simulation, right? But could you imagine doing something where if you had different types of boson scattering, phonons, spin fluctuations of some sort? Can you simulate that? Can you see the differences? Can you imagine that time resolve would be able to disentangle this?
Yes. And in a sense, we've already done this. Because we've done a very simple version. Already done. Okay, boson. Right? That's some kind of charge or spin fluctuation. Now, we haven't done any RPA or anything else that adds to this, but in principle, this is a boson. Right? This is what you do to get spin fluctuations. And yeah, it's very different. Absolutely. If you're in the disordered phase and you make your bosons out of your electrons, you probably can't take energy out of them. Right? Maybe a little bit because the bosons have some heat capacity, right? But not as much as you would have from the lattice. So yeah, they would look very different. But we're working on that.
All right, if there are no more questions, let's thank